Okay, this video is a continuation of examples of mathematical induction that we've been doing. A, B, and C was done in the previous video. We are going to look at D and E here, and then I'm going to give you two examples of your own to exercise your understanding on. Right, so for D, we have the sum from I equals 1 to n of 1 over 2i minus 1 times 2i plus 1. According to this proposition, this is always equal to n over 2n plus 1. Right, the first three terms, so the first term is going to be 1 over 2 times 1 minus 1, 2 times 1 plus 1. The second term is going to be 1 over 2 times 2 minus 1, 2 times 2 plus 1. The third term, 1 over 2 times 3 minus 1, 2 times 3 plus 1, and so the nth term will be 1 over 2n minus 1, 2n plus 1. This is equal to n over 2n plus 1. Right, so the first term, 2 times 1 minus 1 is 1, 2 times 1 plus 1 is 3, and then the second term, 2 times 2 minus 1 is 3, 2 times 2 plus 1 is 5, and 2 times 3 minus 1 is 5, and the other term is 7. So what's happening here is we are summing reciprocals of consecutive pairs of odd integers. So this is equal to n over 2n plus 1. Right, so step 1, we are going to let n equal to 2. So the left hand side is going to be 1 over 3 plus 1 over 15. We can write this all over 15. It's going to be 5 plus 1, 6 over 15. 3 goes twice here and 5 times there. Then the right hand side, we'll plug in 2 here, so it's going to be 2 over 5, which is equal to the left hand side. Hence the formula is true for n equals to 2. Step 2, we are going to assume that 1 over 1 times 3 is 1 over 3 times 5, 1 over 5 times 7 is 1 over 2n minus 1 times 2n plus 1. So we're going to substitute k for all the n's. So we're going to say this is equals to k over 2k plus 1. So assume this is true. for n equals to k, where k is a natural number. Then in step 3, test or prove whether this is going to be true for the next bigger integer. So 1 over 1 times 3, 3 times 5, 5 times 7, then 1 over 2k minus 1, 2k plus 1. Then the next term, we are going to plug in k, k plus 1 in the place of every k. So we're going to have 2 here into k plus 1 minus 1, 2 into k plus 1 plus 1. And then I do the same thing on the right hand side. So the numerator was k, it becomes k plus 1. The denominator, 2 into k plus 1 plus 1. Right, and then let's simplify these two terms here. So 1 over 1 times 3 plus 1 over 3 times 5, 1 over 5 times 7, and so on and so forth, plus 1 over 2k minus 1, 2k plus 1. Then for the next term, 2k plus 1 minus 1, it's going to be 2k plus 2 minus 1, so it's going to be 2k plus 1. This one here is going to be 2k plus 2 plus 1, so it's going to be 2k plus 3. On the right hand side, we are going to have this is supposed to be k plus 1 there. So on the right hand side, k plus 1 in the numerator, denominator, it's going to be 2k plus 2 plus 1, it's going to be 2k plus 3. So I want to test whether this is going to be true. Okay, so again from step 2, we know the sum of the terms up to here. So these terms here are the ones we have in step 2 here, and these are equal to k over 2k plus 1. So this is equals to k over 2k plus 1 from step 2. So what it means is that the left hand side we can write as k over 2k plus 1, and then plus the next term, which is this one here, 2k plus 1 times 2k plus 3. So if this formula is good, this should work out to this term here. So the way to go here is to write this as one fraction. So the LCM is 2k plus 1 into 2k plus 3. This term goes here, 2k plus 3 times. We're going to have k into 2k plus 3, and this term goes here once, so that's going to be 1. So in the numerator we're going to have 2k squared plus 3k plus 1 all over 2k plus 1 into 2k plus 3, and then this numerator we can factorize actually. So that must be 1 and that must be 1. Put plus here. Then we have the 2 factors. Then you are going to see that this cancels out, and then what we have now is the same as the right hand side, 2k plus 3. Okay, so we say hence the formula is true for all values of n which are natural numbers. Okay, the next problem, E, we have the summation of I squared plus 1 times I factorial, I summing from 1 to n. We are told this is equal to n into n plus 1 factorial. So the first 3 terms on the left hand side are going to be 1 squared plus 1 times 1 factorial, then 2 squared plus 1 times 2 factorial, 3 squared plus 1 times 3 factorial, and then term number n is going to be n squared plus 1 times n factorial, and the right hand side is that. Let's simplify these terms. This is just going to be 1 plus 1 times 1. This one, 2 squared is 4 plus 1, 5 times 2. It's going to be 10. This is 3 squared, 9 plus 1, 10. 3 factorial is 6. And then we have here n squared plus 1 times n factorial is equal to that. So that is our formula there. For step 1, let n equal to 2. N equals to 2 on the left hand side, which has 2 terms. 2 plus 10 is 12. On the right hand side, we're going to have 2 into 2 plus 1 factorial is 2 times 3 factorial, 2 times 6. This is 12. This is equals to the left hand side. So hence the formula is true. Then step 2, we are going to assume that, so basically rewrite this formula, that every n is going to be replaced by k, 2 plus 10 plus 60, n squared plus 1 times n factorial is n into n plus 1 factorial. These must be replaced by k. So k factorial and k there. So assume that this is true for n equals to k, where k is a natural number. Then step 3, we want to test whether this formula with one more term will still be good. So 10, 60, this is exactly the same as the term we have here. Then in the next term, this is going to be k plus 1. And this is going to be k plus 1. Okay. And then on the right hand side, we're going to have k plus 1, k plus 1 plus 1 factorial. Let's simplify these two terms. So 2 plus 10 plus 60 a term there is going to be k squared plus 2k plus 2, just k factorial there. And then on the right hand side, we're going to have k plus 1 into k plus 2 factorial. So I want to test whether this is true. Then from step number 2, these terms up to here are equal to k into k plus 1 factorial from step number 2. So therefore the left hand side is going to be k into k plus 1 factorial plus k squared plus 2k plus 2 times k plus 1 factorial. Then k plus 1 factorial is common, so we're going to have k plus 1 factorial into k, which is this one, plus k squared plus 2k plus 2. So this is going to be k plus 1 factorial k squared plus 3k plus 2. This we can factorize. K plus 1 factorial. This is k plus 2 k plus 1. Okay, now so I'm just checking the expression that we are looking for. Then from here, k plus 1 factorial times k plus 2 is actually k plus 2 factorial. So this is not the same as the right hand side, so the formula is going to be true. Hence the formula is true for all n that are natural numbers. Alright, so that's E. I'm just going to give you two that I'd like you to try. while the video is paused, then you can compare your answers with our answers afterwards. So the first one, summation of 4i minus 3 from I equals to 1 to n is equal to n into 2n minus 1. Then summation of 2 to the power 1 minus I from I equals 1 to not infinity but n. This is equals to 2 minus 2 to the power 1 minus n. So just try out these two. Pause the video, then afterwards you can compare with our answers. Alright, so for f, when n is 1, this thing is going to give us 4 times 1 minus 3. When n is 2, 4 times 2 minus 3. When n is 3, 4 times 3 minus 3. Sorry, when I. And then when I is n, it's going to be 4n minus 3. The right hand side is just this one here. Let's simplify this. This gives us 1, it gives us 5, this gives us 9, and that's the term number n. So for step 1, if we let n equals to 2, let's just have these two terms on the left hand side. Gives us 6, we plug into here and here. Also gives us 6, so that tells us that the formula is true for n equals to 2. So go to step number 2, where we assume that this formula is true when n is equals to k. So all that happens here is we simply replace every n here by k. Then we go to step number 3. So now we're going to add one more term after this one. So this term, as you can see, is this one here. To get the next term, where there was k, we plug in k plus 1. Same thing here, where there was k, plug in k plus 1. Where there was k there, plug in k plus 1. Simplifying, this gives us 4k plus 1. This side, that's k plus 1 here, this is going to be 2k plus 1. Then from step 2, these terms up to here are equal to k into 2k minus 1. So that's what we're going to write there. And then we combine these two, we get 2k squared plus 3k plus 1. This can be factorized into k plus 1 to k plus 1, which is the same as this right hand side here. And so that tells us this formula is going to be true for all values of natural numbers. In G, if we plug in I is 1, we get this, plug in I is 2, I is 3, I is n. This is just the right hand side as we have there. It's going to be 2 to the power 0, which is 1. It's minus 1, minus 2 here. The rest are the same. So again, if we try n is 2, the first two terms here will be 1 plus half, which is 3 halves. So if we plug in 2 here, right hand side is going to be 2 minus half, which is 3 halves. So the formula is true for n equals to 2. Then we assume that when n is equals to k, this formula will still be true. Now for the next bigger integer, k plus 1, so we have got all these terms up to this term here. Then for the next term, where there is k, we plug in k plus 1. If we simplify that, it's just going to be 2 to the power minus k here and there. So I want to prove whether that is true. These terms, the first k terms, are equal to this from step 2, so we plug that in there. Now if we break this down to 2 times 2 to the power k, then you can see that 2 to the power negative k is a common factor. If we factorize that, from here we're going to get 1, from here we're going to get minus 2. So that's going to be 2 to the minus k times minus 1, which is simply 2 minus 2 to the minus k. So that's the right hand side, and hence this formula is true.